Start now.
Sounds good. Uh, all right. Can everyone see my screen?
Yes, yes.
Okay, great. Yeah, so thank you for the invitation. I'm going to be talking today about some recent work on reliable methods for agent verification and evaluation. This is joint work with all the people that are on the screen. I'll primarily be talking about a paper that we released in December of last year, but I'll sort of briefly discuss at the end how it relates to some other work, both from myself and from others as well. Okay. So I don't think it's a secret now that everyone is familiar with these agentic LLM models or these agentic models. So some examples are Claude Code, the AI co-scientists. By agent in this setting, I just mean any sort of large model that instead of giving you a single output, it gives you some sort of sequence of actions before it gives you a final output. So like under this definition, logistic regression would not be an agent. But most of the LLMs that you interact with which have some sort of sequential reasoning or sequential action process, would be agents. And so there's this general question on like how to verify their outputs. So nowadays, all of these models make fairly good predictions in lots of tasks, but not in every task. And so how can we verify that, in a particular task or in a particular example task, that they're actually producing a reasonable output? And I think this is a particularly important problem recently because people have observed that while accuracy on various benchmarks is increasing, the reliability is not. And so reliability here, this is just a figure that I pulled from some other paper. Reliability here was some composite index of things like calibration error, robustness, so sort of robustness to distribution shift, and things of that nature. And as you can see on the left side of the plot, the accuracy seems to be, increasing at a much faster pace than the reliability. And so it would be nice to be able to sort of close this accuracy reliability gap and sort of be able to at least give some better confidence on what the output, whether the output is correct or incorrect, or at least provide some robustness. So let's look at what an example verification process might look like currently. So here's a particular example. This is maybe with an AI co-scientist model. So the user asks, find me some chromosome 17 loci that are associated with type 2 diabetes. So basically find me some, region of the genome, within the region of the genome chromosome 17, find me the loci that are associated with type 2 diabetes. So this agent might, have access to some tools, it might be able to write some code. So the first step it does is to retrieve the type 2 diabetes data set. And the second step it does is to subset this data set according to chromosome 17. So both of these seem like reasonable steps. Like they both sort of align with what a user might want if this were the initial query. And so you might ask some sort of reward model or some judge model the probability that each step is correct. So this could either be the probability that that particular step is correct. It could be the probability that every step so far is correct. It could be the probability that the final output will be correct given the steps that it's taken so far. So there's a variety of things that people do with these reward models, but the point is that these sort of process reward models or LLM judges are often used in the generation process itself. So let me just give you a little bit of background on what people do for these verifiers. So how do they train those reward models and LLM judges? So there's kind of three different broad categories of these verifiers. One is LLM as a judge. So this is you just ask another LLM, what's the probability that this is correct, or can you score this partial trajectory that I have so far? The second is process reward model, which is a reward model that's been fine-tuned to provide sort of labels on each step, whether it's correct or not. And the third is outcome reward model, which only provides the reward at the very end of the trajectory. Okay, so one thing that you could do is to just directly try to get a better judge or a better process reward model, for instance, via some reinforcement learning procedure. So an example of what this might be is acquire and train, acquire a bunch of process labels. So for instance, collect a data set of, say, 5,000 math questions, have an LLM solve each math question and give you sort of step-by-step reasoning. Then go in and have a human annotate each of the steps. So if there's 5,000 math problems and on average, each of those takes 10 steps, that would be, 50,000 different steps to annotate. So obviously this is, can be quite inefficient because it requires a lot of labels. And even within each trajectory, it requires multiple like sub-labels. Another thing you could do is sort of directly try to, once you have a PRM, you could directly try to calibrate the PRM, which, process reward models tend to be quite uncalibrated. So maybe you could do something like quantile regression or just build some kind of lightweight calibration technique on top of it. Another line of related work is to sort of directly train the model to stop early. So, for instance, if you know uh, that the generation is likely to be incorrect, you could just train a different model, for instance, to predict whether the current output will be correct or incorrect, or whether it'll match the final output. There's also another line of work on using more conformal prediction procedures to keep sampling until at least one generation is satisfactory. So give like a set of generations such that at least one of the generations in the set is going to be satisfactory. Um, okay, so now sort of back to how that maps on some of those ideas map onto here. So we have this example verification process. Um, And there's sort of two issues. So one is uncalibrated scores. So as I said, some people have tried to address this, but the raw PRMs tend to, or the raw judge LLMs tend to be quite uncalibrated. So this is a example that I ran on two different data sets, and what you can observe is that when the predicted probability is about 80% on both of these data sets, the observed probability of correctness. So this is just asking the LLM like, what do you think the probability that you're correct is? The observed probability is something like, no greater than 40%. And so there's this huge gap in calibration. But maybe the more salient issue is that even if you had calibrated scores, that does not provide you a decision rule or a sequential guarantee on how to use those scores as to decide what to terminate as a sequence. So for instance, if instead of this 0.95, here we observed a 0.2, there's this question of should we continue? And just calibration alone, right? Let's say I was marginally calibrated over all steps or even calibrated within each step, that does not tell me how I should be making decisions about whether to continue my generation or not, just based on those scores. And so we introduced a method called E-valuator, which is a method that can convert any sequentially collected black box heuristics. So we don't make assumptions on how the scores are generated, other than the fact that they're just real valued, um, into a statistical test with controllable error rates. And so basically what that means is that the user can provide some sort of error rate alpha that is desired, and we can return a procedure that will sort of control the error at exactly alpha, or at most alpha. Uh, and one thing that I want to note is that we can adapt this judge or PRM to any distribution. So if you take a PRM that was trained on a completely different distribution, let's say it's trained on math problems, and now you're applying it to chemistry problems, so long as you can provide a fairly small calibration set in the chemistry setting, so for instance, 100 to 200 chemistry calibration problems, we can adapt to that without having white box access to the verifier. So the image that you should have in your head is that there's this running sequence of scores. So the judge is generating scores, S1, S2, so on and so forth. And we're going to convert that into some test statistic, which we'll call MT. And this test statistic will basically be some form of the cumulative evidence that we have so far that the agent is either correct or incorrect. And so, for instance, if the agent is mostly correct, it should stay below some threshold C alpha that we set, which is like C alpha. You can think of it as if the cumulative evidence across all of the steps so far is very strong that the agent is wrong, then it'll go above C alpha. And if there isn't enough evidence, then it should stay below C alpha. And so here's another way of saying that, right? If the agent had instead subsetted to chromosome 18, ideally the judge would have given a score that is lower, and our test will be able to hopefully detect that fairly early on that there is a bad step in this generation, which is likely to throw off this sequence this entire trajectory. Okay. So basically, E-valuator is a way to convert these trajectories that have black box heuristics associated with them from this judge model into a statistical test. Okay, so what do I mean by controllable error rates? So by that I mean we can detect incorrect trajectories at a user-controlled false positive rate alpha or false alarm rate alpha with high probability. So basically the probability that there exists some little t that is less than or equal to capital T, such that m sub little t is greater than or equal to c alpha, given that the agent is correct, is at most alpha. There's a few things I want to point out with this equation. First is that the capital T is not known beforehand. So capital T is basically the number of steps that the agent is going to take. If I knew the number of steps the agent was going to take, my life would be a lot easier, but it could be that on one example, for instance, the agent takes 5 steps. On the next example, it takes 50 steps. So the number of tests I'm going to run is not known beforehand. And the second thing is that this false alarm rate is sort of analogous to the type 1 error rate in sort of classic statistical testing. So we want to minimize the probability of rejecting a trajectory that actually is correct. And of course, you could flip the null and the alternative, and I'll get into exactly what the null and alternative here is, but you could flip the null and alternative to control the other false rate. Okay. And so again, if the flip side of this would be that if the agent is incorrect, so if the agent actually made a mistake, or the final output is likely to be is going to be incorrect, then we can detect that with high probability. Okay. And the summary here is that E-valuator can be used to stop bad generations early, and that saves tokens or rollout costs. So if let's say you're generating a trajectory and you know by step 5 that this is very likely to be a bad generation, there's no reason to continue rolling that out to step 10. So ideally we could save a bunch of tokens and stop that generation early. Okay. So now to formalize the setup, here's how we formalize it just mathematically. So we have h sub t that be the trajectory up to some time t. So this could be the partial trajectory that I've seen so far. This would be, for instance, h sub 2. And S sub t is a function of f of h sub t, which is a heuristic that scores the trajectory. So f could be some judge LLM, it could be some process reward model, it could be some much simpler heuristic. As I said, we assume that f is black box, so we don't know the internals of f, but it provides some outputs s that are, a heuristic for how the trajectory is going so far. And then at the end of the trajectory, there is a label y. So this y indicates whether the final output is correct or incorrect. So for instance, it could be, in this case, with find the chromosome 17 loci associated with type 2 diabetes. At the very end, it's going to give you maybe some list of chromosome 17 loci associated with type 2 diabetes, and you just annotate whether that list is correct or incorrect. We're going to assume binary labels of correct or incorrect right now. This covers a large variety of agentic sort of workflows, but you can think of it as, even in math, it would be basically just verifying whether the final output that you get is correct or incorrect after the entire reasoning process is finished. Okay, and the goal is to construct some sequential decision rule from any black box heuristic to determine if the trajectory is correct or incorrect. And if we can do this well, we could stop bad generations fairly early on. So let S of 1 to t be the sequence of scores from time 1 to time t. So just all of the scores so far from this judge or PRM. So we're going to denote H naught or the null hypothesis as the sequence of scores that I've seen so far is from the set of correct trajectories. And the alternative is that the sequence of scores I've seen so far is from the set of incorrect trajectories. And the assumption here is that if it's from the set of correct trajectory, it's going to follow some distribution P1. And if it's from the incorrect trajectories, it's going to follow some other distribution P0. And so note that, P1 and P2 P1 and P0 may encode arbitrary joint dependencies. So it's not convenient while it would be convenient to sort of assume that this is IID, for instance, all of the scores are IID, or that they might factorize in some clean way. in general, if you're assuming that the verifier or the judge is black box, you can't make these assumptions that might make your life easier, but are actually not true to the process. So it could be that ST and S1 are for instance correlated, dependent in some complex way. And the goal in this setting is to control, what classically we think of as type 1 error, the false alarm rate across the entire sequence. So that's basically the rate at which I call a correct trajectory an incorrect trajectory. So the rate at which I accidentally label examples of the null as the alternative. And the second is high power, right? So this is just how often if it actually is an incorrect trajectory, so if the alternative hypothesis actually is true, what's the rate at which I am rejecting the null? Okay, so here's what we're going to do. So we're going to first collect some trajectories, some scores, and some labels. So, we're going to allow the agent to go on. We're not going to stop during the collection of the calibration set. We're never going to stop the agent. So the agent will just, continue onwards and produce a final answer. And we're going to annotate those final answers. So this will form some calibration set where there's some amount of correct trajectories and some amount of incorrect trajectories. By correct, I mean trajectories whose final output was correct, and by incorrect, I mean trajectories whose final output was incorrect. The second thing we're going to do is we're going to learn the stepwise density ratios. So we're going to set, as I said, we're going to have this test statistic MT. MT is going to be inspired by, basically the likelihood ratio. So it's going to be the likelihood ratio of the sequence of scores that I have, given y equals 0. So given the final output is incorrect, divided by the likelihood ratio if the final output is correct. And I'll get into exactly how we estimate this in a second. But I just want to sort of point out that this is just the likelihood ratio, but just over the entire sequence. So MT is the likelihood ratio of S1 to ST. MT plus 1 would be the likelihood ratio of S1 to ST plus 1, so on and so forth. And you can estimate this using most classifiers, such as the logistic regression. Of course, you're going to incur some estimation penalty, but I'll get into exactly how we control for that estimation penalty later. And then the last thing that we do is we find a threshold to control this false alarm rate. So as I said, MT is this statistic that summarizes the sequence of scores from S1 to ST. And we want to find a threshold, C alpha, such that the probability under the null that MT ever crosses C alpha is controlled at most alpha. So you could either do this using some martingale properties, because the true MT sequence is a martingale, or a conformal approach, and the conformal or a conformal inspired approach. And the conformal inspired approach is going to be robust to estimation error. So I'm not going to dwell too much on E-values, but I did want to talk a little bit about how we got inspiration for this idea. Even though in the end our approach requires a sort of more conformal inspired procedure to control the false alarm rate that we are aiming to control. I do think that this is originally when we were sort of building this paper, this is how we were thinking about it. I do think this set of tools could be interesting, and if someone wants to sort of think about how to use e-values in a more exact way in a similar setting, this could be useful. So let x1 to let x1 x2 be some stream of IID data. This could be a potentially infinite stream of IID data, and I'm testing the null that this sequence is from normal 0, 1, right? So that just it's a bunch of IID samples from normal 0, 1. After every two samples, I'm going to test if it's null or not. So, for instance, I get two samples. Now I'm going to run some tests. I'm sort of abstracting out the test here, the specific test, but assume it's just some reasonable test of normality that I'm running at for instance, some significance level of like alpha equals 0.05 or something like that. So some reasonable procedure that you would run on sort of a single hypothesis test. But in this sequential setting. So I get 2 points. I say, okay, I pass. Then I get two more points. Now my data looks a little bit less potentially normal, but I still don't have enough evidence. So maybe my alpha now is, or maybe my p-value now is like 0.1, and before it was 0.2. So I still don't have enough evidence to reject. And then I get two more points, and now I rerun my test, and now it's, the p-value is 0.01 or something less than my specified alpha level, and I reject the null. And so this should obviously sort of um, make you feel a little bit uncomfortable because this is a form of p-hacking. Uh, because if I were to run this procedure to infinity, I would always reject the null, and you can sort of show that for in a variety of settings that this is true. Um, and assuming the tests are independent, such as Bonferroni, is not okay because the number of tests is not known beforehand. So maybe you've heard of things like Bonferroni or like alpha spending, where you don't allocate an equal share across all of the individual tests. But this in general, none of these procedures will work here because the number of tests is required to is has to be known beforehand. Um, and furthermore, another difficulty is that the p-values themselves are dependent, right? So if I collect, say, 1,000 data points, and my p-value is, say, zero point 0.1, my next after I collect the 1,001st data point, my p-value is not going to be like uniform 0, 1. It's going to be, something very tightly concentrated around zero point 0.1. And so it's because of this dependency you want to, ideally correct for that dependency, but it's kind of hard to combine all of these p-values into a single p-value that is valid across time. So p-values, so just to sort of recap exactly what a p-value is, under the null, it's from any under the null, any p-value is super uniform. So, I mean, for the sake of this, you can just think of it as roughly uniform, but any super uniform distribution. Um, a p-value is a random variable that is distributed as super uniform under the null. Um, for sequential settings, you might use Bonferroni correction or alpha spending or estimate the correlations of p-values. But as I stated, this generally requires that you have some sort of upper bound on the number of tests that you're going to run. Furthermore, you often, typically you need to estimate the null distribution of the test statistic to estimate the thresholds. And so, for instance, here, this is from this tutorial that some people posted online. And as I said, I'm not getting too much in detail on e-values. I encourage you to look at the various tutorials that people have. But they ran this statistical test over multiple sequences, and at the very end, they accidentally rejected the null, even though the null was actually true. So e-values are sort of a modern approach, a modern alternative to this, although many of the ideas in e-values have been around for quite a while. So unlike p-values, the only requirement is that under the null, the expectation of this test statistic is less than or equal to 1. So it can be larger than 1, but the expectation has to be bounded under the null. Furthermore, for sequential settings, you can set up an e-process. So an e-process is some stochastic process, which is M1, M2, etc., um, such that under the null, this is a super martingale. So I'm being slightly imprecise here, but this basically means that the expectation of MT given M1 to T minus 1 is less than or equal to MT minus 1. And because you know this is super martingale, you can use concentration inequalities on martingales to set the threshold under the null. So for instance, there's an inequality called Veal's inequality that applies to that is very popular in the e-process world. And so here's the same test that I showed before, where on the left with the p-values, we accidentally rejected the null, but on the right with e-values, we didn't reject the null. So we were able to correct the fact that we had the sequential hypothesis testing issue where we were rejecting nulls, at some point that we shouldn't have rejected. Okay. So that's like a brief primer on e-values. I think the most important thing that was useful for us is that the number of tests is not known beforehand. And so therefore we got some inspiration from these general ideas. Okay, so back to our setting. Remember that we want to learn these stepwise density ratios. So we want, an empty hat that is approximately equal to, P naught over P1 of S1 to ST. Ideally, we would have the exact, MT equal to P naught over P1, but given that P naught and P1 could encode arbitrary dependencies, the best we can hope for is something that approximately targets this ratio. So how are we going to do that? So observe that, MT if we have the true MT is P naught over P1, we can factorize that using Bayes' rule. So for instance, we could say P of y equals 0 given S1 to ST divided by P of y equals 1 given S1 to ST. So times the prior odds. So P1, P of y equals 1 divided by P of y equals 0. So the first term you could estimate using logistic regression on the calibration set, and the second term you could estimate from the prior odds on the calibration set. So we've now sort of broken out uh, stepwise likelihood ratio into a form that we can estimate empirically from some calibration set. Okay. So why did we choose this test statistic? Well, the reason we chose this test statistic is because, it has nice properties, um, and it's because of those nice properties, it's a good thing to target as the right test statistic. So for instance, the likelihood ratio, one example is the likelihood ratio is a test martingale. And so what that means is that all of those sort of things that I said about e-processes apply to the true likelihood ratio. And again, we don't have the true likelihood ratio, but this sort of is reason to use it as a target. So one is that it's a super martingale, so under the null, it's the condition that I stated earlier. And then the second is that at any stopping time tau, the expectation under the null of m tau is less than or equal to 1. And so, for instance, if you had the true likelihood ratio process, then under the null, you can control the false alarm rate at some user specified alpha. So formally, what that means is that the probability under the null hypothesis that there exists some time. So this time could be is to infinity. It could be anything in the natural numbers. That MT ever crosses 1 over alpha is controlled at most alpha. So for instance, if I set alpha equal to 0.05, then 1 over alpha is 20. So that what this is saying is that if I had the true likelihood ratio process, then under the null, the probability that MT would ever cross the value of 20 is at most 5%. And so that's a nice property of these the likelihood ratio process if you have the true likelihood ratio process. And you can show this very easily by just showing us the test martingale and applying Veals. Maybe the more salient reason why MT is a good target for us to estimate, because we could estimate anything from these scores, is that the likelihood ratio process is log optimal. So this is a result that's been known by Wald and I think Wolfowitz from the 1940s. It's a long known result. Um, but basically, if M prime is any other E process and M be the likelihood ratio process, then at any stopping time tau, the expectation under the alternative of log of m tau is greater than equal to the expectation of log of m prime of tau. And so what that means is that the likelihood ratio process grows fastest among all statistics in log space. So this means that in some sense it's not quite power, right? It's not saying the expectation of m tau itself is greater, but it's saying that it's growing faster in some space that I care about. And and that justifies this as a good target to estimate. Okay, so now let's get to some results. So here we have a few different baselines. The baselines are using the raw verifier. So for the raw verifier, we're just taking the judge scores and trusting them as is and saying, okay, if it ever goes below, for instance, 0.05, I'm going to reject it if my false alarm rate is 0.05. We have a calibrated verifier, which is the same thing, but we just apply, some like isotonic regression or some simple calibration technique on top. And then Bonferroni test, where we, assume that there's some very large number of tests I'm going to run, and Bonferroni correct over that. Okay, so first of all, the green line is E-valuator with the 1 over alpha threshold. So this is using Veal's inequality, which tends to be quite loose. But I want to point out that on the left side, we have the nominal false alarm rate, so the alpha level on the x-axis, and the empirical false alarm rate on the y-axis. And so being below the gray dashed line is ideal, and we are able to be below the gray dashed line, whereas the other methods sometimes are inflating the false alarm rate. On the other hand, we were able to get better power whenever we're able to also control the false alarm rate. So among all the methods that control the false alarm rate, E-valuator in green is controlling is maximizing power. So that's good. But the main thing is that one thing that's concerning about this plot is that there's a huge gap between the nominal false alarm rate and the true false alarm rate. And so uh, ideally, we could close this gap because we're being a lot more conservative than we need to be. And so to correct for this and to correct for the fact that there may be density ratio estimation error, we use just pack thresholding. So we basically are using quantile estimation to find the threshold. So what is our goal? Our goal is to basically, under the null, find a C alpha such that the probability that MT goes above C alpha is controlled at most alpha. An equivalent way to say this is that the maximum of MT hat is the probability that the maximum of MT hat is greater than or equal to C alpha is controlled at most level alpha under the null. And the reason for this is that if the maximum of the sequence never crosses the threshold, then the entire sequence never crosses the threshold, right? If my max is below C alpha, then the entire sequence is below alpha, and therefore I've successfully controlled the false alarm rate. So what's nice is that we actually have access to a calibration set, right? We have access to a calibration set where we have some null samples, so we can estimate these, a distribution of these maxes empirically, and then use some sort of procedure to find C alpha. So the idea that you should have in your head is that there's this null distribution, max of MT hat. There's this martingale-based threshold from Veals, which might be, very far out, might be very conservative. Maybe, in some cases it might be too aggressive. There's no real guarantee that we can directly provide on this given the, potential density ratio estimation error. To control the false alarm rate at level alpha, we just need to estimate the 1 minus alpha quantile. And so we basically want to find a Q hat of 1 minus alpha such that the probability over a draw of the calibration set that Q hat of 1 minus alpha is greater than or equal to Q of 1 minus alpha is at most, is greater than or equal to 1 minus delta. And so we want to estimate a quantile so that the true quantile is below the estimated quantile with high probability. So this is sort of the pack guarantee. And the way we do this is we just find a high probability upper bound on the quantile. It's a very sort of classic binomial argument that probably comes up several times in sort of these like pack estimation procedures. Okay, so now we have the pack version, which is in red, and notice that we've closed the gap. So we're able to be much more aggressive about our test. And this also provides better power. So you can see that the red, sort of dominates green in power here, but it also is able to sort of close the gap between the nominal false alarm rate and the empirical false alarm rate. So here's another example with a different data set. So this is with math and the agent is Claude. So these are with reasoning traces. And again, what we see is sort of a similar pattern where the calibrated verifier or the raw verifier alone don't give guarantees on the false alarm rate. So they might be overly conservative, or maybe sometimes they're too aggressive. But our method, E-valuator, both for the green and the red, is able to control the false alarm rate and is also able to provide fairly good power. So for instance, when the nominal false alarm rate is 0.3, E-valuator with the pack threshold provides empirical power of 0.6. Great. So now I also wanted to visualize what the trajectories look like. So, we have these MTs that we're collecting sort of sequentially. And remember that the target, like the justification for using the likelihood ratio process was that the log growth rate is optimal. So I'm plotting log of MT on the y-axis and the step count on the x-axis. And so these are just a bunch of different trajectories. So everything that was a null trajectory in our test set is in the left side. Everything that's an alternative trajectory or incorrect trajectory is on the right side. And I've set a threshold here of alpha equals 0.1. Don't index too much on the threshold. That's mostly just for visualization purposes. But this is kind of interesting, right? So a lot of the rejections happen very early on. You can see that there's a huge set of red X's after step one, but then there's a reasonably large number of rejections later on as well. So what this is saying is that for at least for math problems, you can detect whether something is wrong or right very quickly, like basically just after the first step. On the other hand, for successful trajectories, there's far fewer rejections as we sort of desire. We also ran on some non-LLM agents. So this was with chess and using stockfish as the verifier. So here, you wouldn't expect the all of unlike in math where, a lot of the rejections are at step one, you wouldn't expect there to be a bunch of rejections at step one because that would basically be saying that immediately after white makes the first move, I have very strong evidence that black is going to win. So that usually doesn't happen. But again, we still see that there is a lot more rejections. So here the alternative is that black wins or ties, and the null is that white wins. And so there's a lot of rejections of the null, but just kind of later on in these games. And by the way, Stockfish is a verifier that basically gives a centipond score, which is just like some numerical score that tells you which I forget the exact bounds of the score, but it tells you whether white is advantaged or black is advantaged, depending on if it's negative or positive. Okay. Another question you might ask is, does calibration set size matter? So here's example with the math trajectory. Kind of all of the lines are overlapping, so you can't really see, but the error bar is on the 5% line. So with n equals 250 is wider than the error bar for n equals 2000. But the rough answer is no. I mean, at least if you went much smaller than this, for instance, let's say you went like with 10 trajectories, I would estimate that yes, the calibration set size would matter, but for, once you get in the hundreds, the calibration set size does not really matter too much. So this is really nice because, at least for the data sets that we tested on, it doesn't really seem like our results are particularly sensitive to the size of the calibration set. Okay, so now going back to sort of the original early termination uh, uh, motivation. So here we did early termination. So basically what we did was we said, okay, we're going to take any time that my test rejects, we're going to immediately kill that trajectory. If the trajectory would have been eventually, correct or accurate, then it's now going to be counted as incorrect. So any correct trajectory can now become incorrect. And then incorrect trajectories were also are still incorrect, but we're going to just count the number of total tokens that were used. Okay. So as a function of the number of total tokens you use, here is, times 10 to the power 5, what is the accuracy? And what we see is relative to using either the calibrated verifier or the raw verifier, E-valuator is able to push sort of this, Pareto frontier, Pareto trade-off between, token usage and accuracy. So for instance, when you use, say, around 80,000 tokens, you can get 50% accuracy on the math data set, whereas with 80,000 tokens and the raw verifier, you can only get around maybe a little bit above 40% accuracy. And this is a finding that we found not just in math, but on other data sets as well, including MLE Pro and some other data sets. Okay, for the sake of time, I'm going to skip this, but basically there is an alternative procedure that you could use. But just in summary, we presented a method that is able to convert any sequential heuristic into a statistical test with guarantees on false alarm rate and power. And we show this on various agents and data sets that it outperforms baselines. And what's nice is that E-valuator can also enable test time scaling. So at the very end, we showed some experiments and have some more experiments in the paper showing that you can sort of push the boundary of token accuracy trade-off um, uh, just by doing sort of these fairly simple statistical tests on the generation itself. One takeaway that I wanted to give you, so this is also came up in some previous work that I did, is that density estimation, like conditional density estimation, is useful for evaluation. So one of the things that we did here, like under the hood, was estimate conditional densities, right? So it's basically estimating what is the density of some judge scores given y equals 0 versus the density of judge scores given y equals 1. And this has come up in the past as well. So in this paper, we were, looking at evaluating multiple models using labeled and unlabeled data, so sort of like a semi-supervised evaluation setting. And there again, what the one of the key insights was that, first you can do some sort of conditional density estimation and then use those conditional density estimates to do some downstream evaluation of either accuracy or expected calibration error. And this is also not a new idea. This is a very old idea of doing sort of conditional density estimation. There's probably papers that are older than this 1977, DeWeed and Skeen paper. But in that paper, for instance, they were also sort of modeling the conditional density of a bunch of different judges given some, true label Y. And using those um, conditional density estimates, they were able to recover, for instance, the ground truth accuracy of each individual judge. And this has come up in not just, old times, but it's also come up more recently, for instance, in the fairness literature and other related literatures. So, if I can leave you with one parting thought, it's that I think, the sort of likelihood ratio um, uh, was well motivated and related to a lot of other things that people have been thinking about in the evaluation world, even if it's not exactly the same. All right, and that's all. And yeah, so thank you to all of my co-authors, and thank you for you all for attending and for inviting me to this talk.